that silvery sheen, that silky sheen on that white part, that white place right in the square in the middle, is pure platinum. The rest is AUPT. And it does all kinds of interesting things. And I think it's going to get more interesting when I get my sandblaster tomorrow. We're moving ahead as we find out how to work with this stuff. This is interesting because although there are small pebbly looking things in there, this black one here and a little, they are in fact just parts of AUPT. And they are not separate at all. They're part of the crystal structure. You can see that, see? It's not like a separate rock, really. It's just sticking up there, and it's a little different color because the mix changes from one part to another. The percentage of gold to platinum changes. It's a solid solution series. And that's why the color of the metal varies from place to place, because the mix changes. Now, in the case of the surface here, we've got some that's raised and some that's lower, and it is all, in fact, I think, the same stuff, or maybe there are variations in the mixture itself across the crystal in this pattern. I don't know. But it's solid metal, the whole thing. Right? I can cut slices of this and mill it and machine it like you do steel or aluminum. And that means I can take pieces like this and cut them and do things like with laser etching and that sort of thing to create pieces that I can use as machine parts, or to, say, make flying wheelchairs. That's what I need. I need a flying wheelchair, and that's the first goal with AUPT, because it is also, in fact, a room temperature superconductor. And it is going to change the world. because we don't have to rape Mother Earth to obtain this metal. It is freely and readily available in quantities beyond anything iron was ever thought of. It is everywhere. And when I melt it, it acts just like any other metal. Like it is here, it's not a metal, it's got covalent bonds. And so it doesn't pass a current, it doesn't, sometimes it's quite brittle. And it's hard as rubies. It is 9 on the Mohs scale of hardness. It is almost as hard as silicon dioxide. Or diamonds. Almost. And maybe some of it is, because this stuff came out of a fault line. And see that? This was a cube. And it got squashed. It's the very definition of being stuck between a rock and a hard spot. It got squashed. And that forces the atoms together into what they call close-packed cubic hexagonal. And that's how diamonds, the carbon atoms in diamonds are arranged. And I'm seeing a lot of the same crystal habits in both. I have diamond crystals the same shape, same exact shape. And so I think this was, once upon a time, a cube. And this side was on one side of the fault, and this side was on the other side of the fault, and it went like so. And there we have it. It made quite an impression on this thing. On both sides. I haven't worked on this side. This side is the way it came out of the ground, or came off of the ground. We picked it up off the surface. See, those little rocks are where the little holes are. Bump, bump. And they're in a very regular arrangement. Bump, bump, bump. And that's because the hoppers are part of the crystal structure in a platinum or an AUPT crystal. Hoppers are the dished out places And if you look really closely inside the hoppers, there's like stair steps or spirals leading towards the center of the that particular cubic arrangement. And so the whole surface of a platinum crystal exhibits these hoppers, these holes, and that's what gives it its patterns. So my wife thought it was concrete, and I was pretty sure it wasn't. And you know, these things are unknown until you really get it home and take a look at it, and that's what we've been doing tonight. And I thank you for joining me.